Hey everyone, my name is Vish, and today we'll go over the homework assignment number one. So let's get straight into it. Sorry that I'm on my bed, but let's get into it. So the first problem is we have to convert the following numbers to binary using a subtraction method. So we have 98 and decimal. We have to convert that to binary something and binary, right? All right, so we know we have 98. Okay, so I'm gonna change this to this way so we can have more surface. So since we know that 2 to the power of 7 is 128, which is bigger than 98, that's a good thing. And 2 to the power of 6 is 64. All right, so 98 is in between 128 and 64. That means we need at least 8 bits. Why do I say 8 bits? Because we're gonna start counting from 0, 1, 2, 3, 4, 5, 6, 7. That's 8. So we need at least 8 bits to express this 98 in decimals to binary. Sounds right. Okay, so we're gonna say 2 to the 7, 2 to the 6, 2 to the 5, 2 to the 4, 2 to the 3, 2 to the 2, 2 to the 1, 2 to the 0. So this is 128, this is 64, 32, 16, 8, 4, 2, and 1. Alrighty. Now, so for the subtraction method, we're gonna try to subtract these numbers from this. But here's the thing. So when we subtract, we need a positive answer. We don't want a negative answer as a result, as a remainder of that. Okay, so if we subtract 98 minus 128, that's gonna be a negative number. So we cannot do that. So since we cannot do that, we're gonna say we haven't used this just for subtraction. And if we do 98 minus 64, that's a positive number. So we can say 98 minus 64, that gives us 34. Awesome. Since we use the 64, we're going to put this as 1. And let me move this a little down so we have enough space. All right. Now 30. Now we can now 32 on to the next number, 32. So we can do 34 minus 32 because that will give us a positive number. That's 2. So we used this number as well. We're going to say we used it. Okay. Now 2 minus 16 will give us a negative number. So we cannot use this. 2 minus 8, negative number. We cannot use this. 2 minus 4, a negative number. We cannot use it. 2 minus 2, we don't get a negative number. So 2 minus 2 equals to 0. So we use this 0. Here's the thing. For this course, we're going to think that 0 is a positive number. We're going to assume that 0 is a positive number. And later on, if you keep doing more work on computer architecture, you will realize that you can have a positive and a negative 0. But for at this moment, that's out of your scope. So let's just focus and say that 0 is a positive number. So since we used this 2 minus 2 here, we're gonna say 1. We're gonna say we used it, so we're gonna put 1 here. Now we have 0. 0 minus 1 is a negative number, so we cannot use this. So this is 0. There you go. That's it. So our let's divide them into 4 bits each. So 98 in decimal is equal to 0110 0010 in binary. That was our first problem. All right. Second one. We have 1045 in decimal. We have to convert that into binary. So we know 2 to the power of 7 is 128, which is way, way, way smaller than 1045. Okay, so we can, let's assume 2 to the power of 10. Let's see what that is. It's 1024. It's smaller than 1045. So what that means, if we use 11 bits in binary, that can only express number up to 1024. But 1045 is bigger than that. So we might need a bigger number to express that. Okay, so let's say 2 to the 11. What's that? That's 2048. So this means with 12 bits of binary number, we can express up to this much of decimal number. So yeah, so this means we have to use this number, like this many binary bits to express 1045. All right. So instead of writing 2 to the 11, I'm going to just write it as 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Sounds fair? Okay. We know 2 to the 11 is 2048. 2 to the 10 is 1024. 2 to the 9 is 512. 2 to the 8 is 256. Then 1 to 8. Then 64, then 32, 16, 8, 4, 2, 1. All right. So 1045 minus 2048, it's going to give us a negative number. So we cannot use that. So we're going to put a 0 here. 1045 minus 1024, that will give us a positive number. So which comes out to be 21. Since we used this for subtraction, we're going to put this one here. Let me move this again at the bottom. All right. Now 21. So 512, we cannot use this. 21 minus 512 is a negative number. It will give it a negative number. 128 will give us a negative number. 64 will give us a negative number. 32 will give us a negative number. Now 21 minus 16 will give us a positive number. So we can use that bit, that place. So we're going to put this one because we subtracted. All right. Now 5 minus 8, negative number. 5 minus 4, this will give us a positive number here. So we can say we used this. 1 minus 2, negative number. We cannot use that. 1 minus 1, 0. So we use this. So this means let's divide them into 4 bits each. And there you go. So 1045 in decimal is 0100 0001 0101 and binary. I hope I'm not going too fast because you already have learned this thing in your class. I'm just going over the homework problems. So, but let me know if I'm going too fast. Okay, the third problem is 254 in decimals. Okay, let's look back here. So we know here is 256. And if we use 9 bits of binary, because there are 9 numbers, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, right? If we use 9 bits of binary number, that can express up to 256 in decimal. And R is 254. So that means all we need are 9 bits. So let's write them down. 8, 7, 6, 5, 4, 3, 2, 1, 0. We know it's 256, 128, then 64, then 32, then 16, 8, 4, 2, 1. Awesome. So since it's 254, we cannot, 254 minus 256 is a negative number. So we cannot use that. Okay. Oh, and I messed up on my notes for some reason. I did subtract them. I don't know why. Sorry about that. Okay, but 254, we can subtract 128 out of 254. This will give us a positive number. So it becomes 126. So we used this. Here we go, 1. Now 126 is greater than 64, so we can subtract them without getting a negative number. I mean, you can even subtract 254 and 256, but that will give you a negative number. That's why we are trying to avoid that. But in this case, 126 minus 64 gives us a positive number, which is 62. So we used this number to subtract as well. Now 62 minus 32, because it will give us a positive number. So we use this, it becomes 30. Now 30 minus 16 also gives us a positive number. So we used this bit, which is 14. 14 minus 8 will give us a positive number, which is 6 over here. Now 6 minus 4 gives us a positive number 2. So we used this bit here as well. 2 minus 2 gives us 0. We used this one. 0 minus 1 gives us negative. So we cannot use that. So here you go. Let's divide them into 4 bits. There you go. So 254 and decimal is equal to 0, 1, 1, 1, 4 ones, 1, 1, 1, 0, and binary. So that was our first problem. And let me show you something really neat about everything, like about this problem. So if you look at this number, it's an even number, right? So whenever you have an even number in binary, your last bit should always be a 0. If decimal is even, then binary conversion should also give you the least significant bit in the binary number should be a 0. 1045, it's an odd number. And for odd numbers, our last bit, the least significant bit, should always be a 1. So keep that in mind. Now look at this. Here we have an even number. What do you think the least significant bit of 254 in binary would be? Here, even was 0. So what do you think over here is going to be? Yes, it's going to be a 0. So this is a nice trick to keep in mind when solving this. It doesn't give you the exact answer. Knowing this trick doesn't help you solve anything, but it's just an extra step to make sure that you're on the right track. Even at this point of my life, whenever I do a conversion, I always check the least significant bit, because if my number in decimal is an even number and my binary's least significant bit is 1, that means I messed up somewhere. It's just an, I don't know, kind of verification that you're on the right track. But yeah. Okay, on to the next problem. The next problem is convert the following binary using the division method. Okay, so I know this is your introductory class to all this stuff. That's why you need to learn subtraction method. But personally, everyone that I know in upper division courses, they never use a subtraction method. They always prefer division method. And the reason being is, for subtraction method, you need to know like a lot of stuff, like a lot of 2 to the 8, 2 to the 10, 2 to the 11. And we are engineers. We don't want to remember that much stuff. That's why we chose engineering. So, but we all of us use a division method more than as compared to subtraction method. So let's do division method now. The first problem is 55 in decimals. So division method is pretty simple. You're gonna do this, 55. Okay, I'm gonna show you a neat trick when dealing with division methods. Okay, so in lectures and everywhere, every book will tell you a different method, but this is from my own personal experience. Like, I use this trick a lot and it helps me a lot too. It saves a lot of time for me, I guess. So here's the thing. When doing with the division method, so you're gonna divide whatever number is with 2. Sound okay? And watch, if that number is an odd number, remember all the time you're gonna have a remainder of 1 here. Every time. Just take this to the bank. If it's an odd number and you're doing a division method, whenever you see odd number, just put a 1 here automatically. Don't even think about it. Okay, now we're gonna do this. We're gonna solve it. So we know 55 divided by 2 will give us, let me use my calculator real quick. So you're going to do 55 divided by 2. It gives us 27.5. So we're going to ignore the decimal position. We're just going to write 27 here. All right. Then we're going to divide it by 2 again. 27 again is an odd number. Let me use a different color so we can. Okay, let me do it again. So I have enough space to do it. So 55 divided by 2. Since it's an odd number, I'm going to just put 1 here without even thinking anything. 55 divided by 2 is 27.5. So I'm going to just write 27 here. Now divide by 2 again. 27 is an odd number again. So I'm going to just put 1 here again. And 27 divided by 2 is 13.5. I'm going to just write 13. Divide by 2 again. 13 is an odd number. I'm going to put 1 more again. 13 divided by 2 is 6.5, but I'm going to just write 6. Crap. Let me find my charger. That's why I like my bed, actually. Charger's right there. All right. So 13 divided by 2 is 6. 6.5. So I'm gonna just write 6 and put 1 here. Okay, now 2. 6 is an even number. So whenever there is an odd number, I'm just gonna put 1. But if it's an even number, I'm gonna just put 0 without even thinking. 6 divided by 2 is 3. Okay, then 2 again. 2 divided by 3 is 1.5. I'm gonna just write 1. And since it was an odd number, I'm gonna just put 1 here. 2 divided by 1 is 0.5, right? So I'm gonna write 0 here. And since it's an odd number, I'm gonna put 1. Once you read 0, that's it. That's it for you. Now, for this, we're gonna write this from bottom up. So let's divide them into 4 bits. There you go. So this means 55 in decimal is equal to 110111 in binary. That's a trick. That's it. That's how you solve it. Now let's do the next problem. It's 188 in decimal. Let's use the same method to solve it. 188 is an even number, so I'm gonna put 0 here. 188 divided by 2 is 94. 94 is an even number. I'm gonna put 0 again. 94 divided by 2 is 47. Okay, 47 is an odd number, so I'm gonna put 1 here. 47 divided by 2 is 23. 23 is an odd number. I'm gonna put 1. 23 divided by 2 is 11.5. So I'm gonna put 11. 2. 11 is an odd number. I'm gonna put 1 here again. 11 divided by 2 is 5.5. Okay, 5 is an odd number. I'm gonna put 1 here. 5 divided by 2 is 2.5. So I'm gonna put 2 here. 2 is an even number, so 0. 2 divided by 2 is 1. Now 1 is an odd number. I'm gonna put 1 here. 1 divided by 2 is 0.5. Here you go. And let's divide them into 4 bits. So 188 in decimal is actually equal to, we're gonna go from bottom up, 10111100. There you go. That's our conversion using division method. Now, here's another thing. Let's verify the trick that I showed you in the first problem. Here, 55 is an odd number, right? And look at the last bit. It's 1. Here, 188 is an even number, and the last bit is 0. So it's always true, no matter what. Okay, now on to the next problem. Okay, the next problem is 933 in decimal. Okay, 933 in decimal. Okay, let's do it again. 933. It's an odd number. So 1 divided by 2 gives us 466.5. I'm gonna just write 466. Divide by 2 again. 466 is an even number. So divide that, it becomes 233, which is an odd number. So 1 233 divided by 2 gives us 116.5, which is an even number, so 0. 116 divided by 2 gives us 58, which is an even number, so 0. 58 divided by 2 is 29. 29 is an odd number, so here you go. 29 divided by 2 is 14.5. So 14. 14 is an even number, so 0. 14 divided by 2 is 7. 7 is an odd number, so this, we put 1 here. 7 divided by 2 is 3.5. I'm going to just write 3. 3 is an odd number, so 1. 3 divided by 2 is 1.5, so I'm going to write 1 here. 2, 1 is an odd number, so 1. 2 divided by 1 is 0.5, 0. There you go. So that's it. So we're gonna divide them into 4s. Okay, so 933 in binary is 1 1 1 0 1 0 0 1 0 1. And since 933 was an odd number, we get least significant bit as 1. And the last problem, 1 0 3 4 5. Let me verify something. Yep, that's it. 1 oh. 1 3. Oh, I got it wrong. Hold up. So sorry. So I did this math off screen because I don't want to waste your time doing simple math. So 1 3. But I'll just go over it real quick with you guys so that you can have an idea. So this was an odd number. I put 1 here. Divided by 2 gives me 6522.5, which is an even number, so 0. And I kept on doing that until I got 0. So I think it's just a basic math. You have an idea about this. It's like similar to these problems, but it's just a little bit longer. There is nothing any special about this problem. So I just did the math by myself. So odd 1, even 0, odd 1, odd 1, odd 1, odd 1, 0. Like it's the same thing. So, but at the end, I'm gonna just write the results. I'm gonna divide them into 4 patterns each. So and bottom up. So it becomes 1 1 0 0 1 0 1 1 1 1 0 1 0 1. That's in binary for this number. I again, it's an odd number. I get least significant bit as 1. Okay, so on to the next problem. So we have to convert the following binary numbers into decimal. So the first binary number is 10110110. So the trick for these problem is how I usually do it. I number them. So this is 0th place, this is 1st place, this is 2nd place, this is 3rd place, this is 4th place, this is 5th place, this is 6th place, this is 7th place. So what I'm gonna do, I just gonna write the numbers that has 1 on it. I'm gonna write the numbers, like I'm gonna write the positions that has a value of 1 to it. So for example, in this case, 2 to the 7th is 1. So I'm gonna write 2 to the 7th. 2 to the 6th is 0. I'm gonna ignore it. 2 to the 5th is 1, so I'm gonna write that. 2 to the 4th is 1, I'm gonna write that. 2 to the 3rd is 0. I'm gonna ignore that. 2 to the 2 is 1, so I'm gonna write that. 2 to the 1 is 1, so I'm gonna write that. 2 to the 0 is 0, so I'm gonna write this. And if you add them up using your calculator, you should get 182, which is the value of this binary, but in decimal. So it's simple. You're gonna write the binary number, you're gonna number each bit starting from 0 up until it goes. Then you're gonna ignore every position that has 0 value to it, and you just gonna use the positions that has a value of 1. Once you do that, you're gonna add 2 to the power of whatever position that has a value of 1, and then add all those positions together. 2 to the power of that position together. For example, the next one is 1101. In this case, I have 0th position, first position, second position, and third position. We have only 4 positions in this case. So how I'm gonna do this, I'm gonna say, so the third position has a value of 1. So I'm gonna write 2 to the 3, then add it to the next position that has a value of 1. In this case, it's 2 to the power of 2. So 2 to the power of 2 is 1. 2 to the power of 1 is 0. So I'm just gonna ignore this. And at 0th place, we have 1. So I'm gonna say 2 to the 0, right? So this gives me 13. Here, look at this again. So in this case, the least significant bit was 0, and the number is even. So that law still stands, that rule still stands. If the least significant bit is 0, the number should be even in decimal. Similarly, here the least significant bit was 1, and the number is odd. There you go, again. And our last problem in this question is 0, 1, 1, 1, 0, 1. I'm gonna position them again. So this is 0th position, this is first, this is second, this is third, this is 4th, this is 5th. So we have a 6-bit number, and we're gonna do the same thing we were doing. So 2 to the 5 is 0. We're gonna ignore that. 2 to the 4th is 1. So I'm gonna say 2 to the 4 plus 2 to the 3 is 1. 2 to the 3 plus 2 to the 2 is 1. So 2 to the 2. 2 to the 1 is 0. So I'm gonna ignore that. And plus 2 to the 0. And if you add all these numbers, it comes out to be 29, which is an odd number. And this makes sense since the least significant bit is 1, and it's an odd number. So that explains. All right. So these were the problem related to binary. Now the next one is we have to convert the numbers from decimal to hexadecimal. So this is number, we have to find a value in base 16. Okay. So for the first problem, so how I do these kind of problem, it's similar to the binary conversion. So I have 45, but instead of dividing it by 2, I'm gonna divide it by 16. Okay, now if you divide 45 by 16 on your calculators, you can say 45 divided by 16, that gives me 2.8125. But we don't care about anything beyond the decimal position. So I'm gonna just write 2 here. Okay, right? Now 2 multiplied by 16 is 32, right? 2 multiplied by 16 is 32. Since I got this 2 from here, and this 16 is from here. Makes sense? So I have 32. Now, what I'm gonna do is 45 minus 32, which gives me 13. So the remainder is 13. So I'm gonna write this, 13. So we cannot divide 16 by 2. So there's it. So we're not gonna do it. We're not gonna do it. If it's less than, yeah, we're not gonna do it. We can just leave it as it is. So 45 in decimal is 2. We're gonna again go from up like this, 213 in 16. But here's the thing, there is no such thing as 13 in hexadecimal. What do we have is 0 through 9. Then instead of 10, we write A. Instead of 11, we write B. Instead of 13, we write C. And we go until F, which is 15. So since we have a 13 here, instead of writing 13, I can write this as C. So 45 in hexadecimal is 2 C. Actually, it's D. So this is 10, this is 11, this is 12. So D is 13. So I'm gonna write this as 2D in hexadecimal. I hope that makes sense, but let's do the next problem because that will make like practice will make you better. So the next problem is 909 in decimal. Okay, let's do that. So if you do 909 divided by 16, if you use your calculator, it's gonna give you 56 point something, something, something. 56 point something, whatever, okay? And if you do 16 multiplied by 56, again, I got this 16 from here, and this 56 is from here. This 56 is from this 56. 16 times 56 is 896. Now, 909 minus 896 gives us 13 again, which is, we know 13 is D. So instead of writing 13 as a remainder, we're going to just write D. Now, 56. If you do 56 divided by 16, you're going to get 3 point something, but we don't care about the points. So it's going to be just 3 itself. Now, 16 multiplied by 3 gives us 48. Now, 56 minus 48 to check the remainder is 8. So you're going to write 8 here. That's it. We can, because 3 is smaller than 16, we're not going to solve it. We're just going to leave it as it is. So 909 in decimal is equal to, going bottom to up, 38D in hexadecimal. There you go. Let's do the next one, 567 in decimals. We're going to do the same thing, 567 divided by 16. So if you do the math, you're going to get, using calculator, you're going to get 35 point something. We don't care about the something part. So we're going to do 16 multiplied by 35, which is, wow, I need to use my calculator. I thought I did the math, but anyway. So 16 multiplied by 35 is 560. And to get the remainder, we're going to say 567 minus 560, which is 7. So the remainder is 7. Now, if you divide 35 by 16, you're going to get 2 point something. So you can leave that it is. Now, 16 multiplied by 2 is 32. So 35 minus 32 is 3. So the remainder is 3. Since 2 is smaller than 16, we're just going to leave it as it is. So this means going bottom to up. 567 in decimal is 237 in hexadecimal. I hope this makes sense. I know it's a little bit different from that of the binary conversion, but it's kind of the same thing. The only difference, it might seem a little harder because in this case, in binary conversion, in this case, our remainders were just 1 0 1 0 1 0, and we were doing that on basis of even and odd numbers. But in 16-bit, in hexadecimal, it gets a little complicated. So you have to do a little more work to find the remainders, to find what's left after the division. So that's where you add these 2 steps. But other than that, it's the kind of same concept. Okay, and on to the next one. Okay, the next problem is we have to convert the hexadecimal numbers to decimal. So base 16 to base 10. So the first problem, oh, what happened? Okay, so the first problem is AEF. AEF in 16 to something in decimal. Okay, so we know that A is 10, B is 11, C is 12, D is 13, E is 14, and F is 15. So remember this. Okay, we're gonna use this a bit in our calculations. So this one is similar to binary conversion, but binary to decimal conversion, the only difference is in binary conversion, we let go of the numbers that has a zero value. We let go of the places that has zero value. In this case, we can't do that because these numbers have some value more than zero. So what we're gonna do, it's kind of similar to that. We gotta write the position. So this is zeroth position, this is first, this is second. Awesome. So we're gonna say the first, the A, this position, the most significant bit, A multiplied by 16 to the power of 2. So this A is the most significant bit. This 2 came because A is at the second place, or the third bit of this number, of this hexadecimal number, plus E multiplied by 16 to the power of 1. Reason being, this E is at the first position. So we can write this as this, plus F multiplied by 16 to the power of 0, because it's a least significant bit, which means the place is 0th. So F multiplied by 16 to them. This means A has a value of 10. So 10 multiplied by 16 to the 2 plus E, which has a value of 14, multiplied by 16, plus F, which has a value of 15, multiplied by 16 to the 0, which is basically 1. So I'm going to just write 15, if that makes sense. And if you add them all together, I have 2799 in 10th. So this means AEF in 16 is equal to 2799 in decimal. Okay, let's do another problem. 1C34. We're gonna assign positions again. So this is zeroth position, this is first, this is second, this is third. We're gonna do the similar thing. So 1 multiplied by 16 to the 3, because 1 is at the third position, or like on the third position, right? Plus C, which is at the second position. So we're gonna write 2 plus 3, which is at the first position. So write 1 plus 4, which is at the zeroth position. Since C has a value of 12, I'm gonna just convert that to 12, and it becomes 16 to the 3 plus 12 multiplied by 16 to the 2 plus 3 multiplied by 16 plus 4. And the total comes out to be 7220 in decimal. So this means this value is equal to this. And this hexadecimal value has a decimal value of this. And another one is BED in 16. So we're gonna assign positions first. This is the zeroth position, this is the first, this is the second. So this means B multiplied by 16 to the 2 plus E multiplied by 16 to the 1 plus D multiplied by 16 to the 0. B is 11, E is 14, and D is 13. You can look it up over here in this chart. And okay, so if you do the math, 16 multiplied by 256 plus 14 multiplied by 16 plus 13, this comes out to be 3053, which is the value of BED in hexadecimal. So it's pretty straightforward and it makes a lot of sense. Now, on to the next problem. Convert the following hexadecimal to binary and explain how you did it. Okay, here's a nice trick to do these problems. And the trick goes like this. So first you're going to write the number D4E in hexadecimal. We know D is basically 13. 4 is 4 and E is 14, right? So instead of converting D4E to binary, we're gonna just write their appropriate values first. Then we know 13, we can easily, instead of writing D4E into binary, which is you can do it, but it's like a longer way to do it. Like you can easily convert 13 to binary, right? What you simply do, 13 divided by 2, it's an odd number, so 1, which gives us 6.5. It's an even number, so 0. And it gives us 3, which is an odd number, and it gives us 1, which is an odd number, 2, 0. So 13 in binary is 1, 1, 0, 1. 4 in binary similarly is 0, 1, 0, 0. And 14 in binary is 1, 1, 1, 0. So I think you can do this easily. So D is 13, 4 is 4, and E is 14, right? And these are their appropriate binary of single terms. So once you find these numbers, you can just combine them together. So it becomes 1, 1, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0. So this means D4E in hexadecimal is equal to 1, 1, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0 in binary. There you go. So you don't have to divide anything by 16 anymore. Like technically, if you have to do it like this similar way, like we've been doing, I thought we did some. I guess I'm tripping. But anyway, my point is you don't have to, like, for example, over here we've been multiplying by 16. So technically, in order to convert, just scratch that. Don't worry about that. So basically what I'm trying to say is once you know the hexadecimal number, but if there are anything that needs to be converted to a simpler form, like A to 10, B to 11, C to 12, D to 13, blah, 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 like that, do the simplification first. And then from that simplified number, convert each number to its binary equivalent and add all those numbers together. For example, let's do another problem. Let's say 293B in hexadecimal. So 2 is 2 in hexa, 9 is 9, 3 is 3, but B is 11. Okay, so and if you do the decimal to binary conversion of this number, 2 is basically 0010, 9 is 1001, 3 is 0011, and 11 is 1011. So we can just combine them all together. There you go. That's our binary of this number. Okay, it might be possible that I might be bad at explaining some stuff because it's my first time explaining this kind of stuff. So let me know if it doesn't make sense. I can try to explain it much better. But yeah, okay. So 130E and the last problem. This is in hexadecimal, so space 16. So we're gonna simplify each number. 1 is 1, 3 is 3, 0 is 0, and the E is 14, right? So you're gonna convert these numbers to binary. So 1 is 0001, 3 is 0011, 0 is 0000, and 14 in binary is 1110. So once you're done with that conversion, you can just add up all the numbers. There you go. That's the binary equivalent of hexadecimal. Like they are the same. So I hope this helps. And ask me or shoot me an email if you need some further clarifications. And oh, actually, there's one last problem. It says, why do we use hexadecimal numbers? So the reason being why we do use hexadecimal numbers is pretty simple. Look at it. Look at these problems. We have BED that represents 3053. 3053 is a big number to express, but instead we can use BED in place of 3053 that do less. It's less workload for computer. It saves memory. It saves time, if that makes kind of sense. Like you can represent really big decimal or really big binary numbers into small hexadecimal numbers. It saves time and memory a lot in computer processor. So that's why we prefer hexadecimal positions, because it's easy. Because think about it. Let's say if you're dealing with a memory position, right? Memories are really big. It has like gigabytes, even in terabytes. A gigabyte is 10 to the power 9. So think about it. If a computer is communicating with you through assembly language, you're dealing with assembly, you're saying that, oh, the integer x is at some location in memory. So do you want computer to give you a big number that you're gonna struggle to read and stuff, or you want computer to give you a smaller number that's easier for you to remember? I think you would say smaller number, right? So I hope so. But yeah, that's why we use hexadecimal numbers, because we can represent really big decimals or really big binary numbers into a smaller, concise hexadecimal numbers. So I hope this helps. Thank you.